Hello, everyone. Welcome for my presentation. By name, call me Duncan Eregan Ronald, and I will be taking you through memory management in operating systems. Under this topic, we shall be able to understand the basics of memory management. We shall also understand address mapping. We shall understand how memory is being allocated to different processes in the operating system. We shall also understand the fragmentation, compaction, purging. We shall understand basics of virtual memory. And finally, we shall understand trusting in memory management. Memory management, by definition, is a process of controlling and managing functionality of a RAM. Why do we need this memory management? We need this memory management to keep track of the status of each memory location, whether it is allocated or free. It also enables computer systems to run programs that require more main memory than the amount of free main memory available on the computer system. For example, let's have a computer with, for example, a computer with a free memory of 3 GBs running a process that requires 6 GBs. Memory management also addresses the system's primary memory by providing abstractions. I think this one is self-explanatory. It also protects the memory being allocated to all the processes from being corrupted. This is mostly done by adding an extra bit to the page frames. And then it also enables sharing of memory spaces among processes. Address mapping, this one is subdivided into two. We have the logical address and then the physical address. The logical address, it represents the location of data in the logical space, and these are generated by the CPU during a program execution. And then the physical address represents the actual location of data in the computer's physical memory. Hadoop. In simple terms, we can say physical address is a direct reference to a specific memory cell. Let me just show you a diagrammatic illustration of how the logical address, the physical address relates to the CPU and the main memory, how they are interconnected. So let's say we have, this is our CPU, this block, this box. Let's call it our CPU. And then we have our main memory verified here. Well, the aim is the CPU accessing data from the main memory. So this is our main memory. And then in between, how do these two communicate? They will need our memory management unit, that is the MMU, to interconnect the two. MMU. And then the CPU here generates the logical address. And then here in the main memory, we have our physical address. So this is how the CPU, the memory management unit, and the main memory interrelate in a computer system. What is the importance of this address mapping? Address mapping establishes the relationship between the logical and the physical addresses, and it is essential for efficient memory management in operating systems. Let's go to memory allocation. Under memory allocation today, we shall only focus on the contiguous memory allocation. By definition, this is a memory management technique that involves allocation of a process to the entire contiguous block of the main memory it requires to execute. This means that the process is loaded into a single continuous chunk of memory. Contiguous memory allocation is divided into two parts. We have the multiple partition allocation, and then have the fixed partition allocation. The multiple partition allocation, in this method, a process is selected from the input queue and loaded into the free partition. When the process terminates, the partition becomes available for other processes, meaning immediately after the process terminating, its memory it had occupied is then unveiled for other processes to also access and use. And then for the fixed partition, in this method, the operating system maintains a table that indicates which parts of memory are available and which are occupied by other processes. Fragmentation. Fragmentation, by definition, refers to the inefficient utilization of memory space, leading to unusable memory. External and internal are the primary two types of fragmentation. I think for me to explain this, let me use an example. Let's take an example of a block of memory, a memory block of fixed size. Let's say the size is 12 MBs. This is block size. Our total block size is 12 MBs. Then this block is being partitioned into three parts. We can name them as B1, B2, and B3. This is B1. This is B2. This we can call it B3. And then B1 has been allocated a space of a memory of 4 MBs. B2 is being allocated a memory of 3 MBs. And then B3 is being given a memory of 5 MBs. In B1, we have a process that is P1 using a memory of 1 MB, causing internal fragmentation of 3 MBs. So this is internal fragmentation. Let me just identify it uniquely by shading it. Yeah, so 3 MBs. And then in block B2, we have a process also P2. Process P2. Process P2. Process P2 using a memory of 2 MBs, leaving causing internal fragmentation of 1 MB. This is internal fragmentation, 1 MB. Let me set it. And then for block size 3, for the block 3 of size 5, we have a process P3. Process P3 using a memory of 4 MBs, causing still internal fragmentation of 1 MB. So I think I can say this. So this is internal fragmentation of 1 MB. So the total internal fragmentation in our block of size 12, it will be the 3 in B1 plus the 1 in B2 plus the 1 in B3, totaling to internal fragmentation of 5. Internal fragmentation of 5 MBs. So let us assume that there is a process P4 that there's a process P4 that requires a memory of 5 MBs. So this process P5 will not be able to be allocated the memory because of the speed of the available memory, 5 MBs in the block size of 12, hence causing an external fragmentation of 5 MBs. Fragmentation of 5 MBs. So external fragmentation, so all out of memory space is sufficient to dwell a procedure in it. However, it isn't adjacent, so it can't be utilized. So that explains that term. The sentence, the paragraph are given under external fragmentation. So here you can see that our unallocated memory is 5, but then still a process P5 cannot still use this 5 unallocated memory because of the speed of the available memory. The speed of the available memory. Let me just wrap this off as we go to the next slide. Then we shall learn about the compaction. By definition, compaction is a technique used to reduce fragmentation and optimize the use of memory space. So we are bringing compaction so that now we reduce the speed of available memory, how the unallocated memory to reduce on the contiguous unallocated memory. So meaning we using a compaction, we are going to gather all the unallocated memory on one end, and then the used memory on the other end, so that when you have another process, it can be able to use this unallocated memory. So what is the importance of this compaction? It addresses the internal fragmentation by consolidating and compacting allocated memory blocks. It also mitigates external fragmentation by rearranging and consolidating free memory blocks, rearranging, as we were seeing in the previous slide. Fragmentation. So this was an image of a fragmented memory block, whereby this is a used memory, this is an unused memory, this is a used, this is used, this is unused. So meaning this one is a chunk allocated but then fully utilized, this one allocated, not fully utilized. So using by applying compaction, we shall now collect all these unutilized on one side and then the utilized on the other side, so that we can make use of the unutilized. Let's learn about purging. Purging is a memory management scheme that eliminates the need for contiguous allocation of physical memory. The system divides the memory into fixed size of blocks. The system divides memory into fixed size of blocks called purges, and logical memory of the same size known as frames. The principle of operation involves these pages to frames, enabling non-contiguous storage of processes in physical memory. Paging systems assumes an essential job in actualizing the virtual memory. So what is the process in allocating in allocation in paging? Well, when a process is loaded into memory, it is divided into fixed size pages. These pages are allocated to available frames in the physical memory. The operating system then maintains a page table to track the mapping between the logical and the physical addresses, allowing for efficient retrieval of stored data in the non-contiguous memory locations. Hardware support for purging, I think this one it's self-understandable. We have only two here for now. We have the purge table, which is a critical hardware component that stores mapping between a logical and physical address, and then have the memory management unit that is responsible for translating logical addresses into physical addresses during memory management. What is the role of this operating system in the hardware support for purging? Operating system helps in purge fault handling, and then it also helps in the purge replacement policies. So protection and sharing, I think this one you can understand it. It's self-understandable. The advantages and disadvantages of purging, I think these ones are easy here. Is a rundown of favorable circumstances. So here, the advantages of purging decreases outer discontinuity, yet at the same time experience the ill effects of the inside factor. Another advantage is that purging is easy to actualize and expected productive memory for the board method. Due to the parallel side of the purges and this, swapping turns out to be simple as the last advantage. Now, disadvantage of purging is that a purge table requires additional memory space, so may not be useful for a framework having a little RAM. The basics of a virtual memory, I think we have learned about this in the previous slide, so I won't talk much here. And by definition, virtual memory is a technique that allows the execution of processes that may not be completely in memory. Program can run larger than the physical memory. What are the advantages of this? Less I/O would be needed to load each user program into memory. More programs could be run at the same time, with corresponding increase in CPU utilization and throughput, but with no increase in response time. For instance, let's assume I have a computer, a laptop of 4 GB RAM that is running a process of that is running Adobe Photoshop and Adobe Illustrator at the same time. So also programs would no longer be constrained by the amount of physical memory. Yes. So trusting, I think this one we can read. Demand, this one we can read. They are easy. And then path placement policies, we have here we're only going to learn about the three, the FIFO, the LRIU, and then the OPRA. So the LRIU is associated with each page and the time when that page was brought into memory, and then the LRIU list recently used associates with each page and the same time. Thank you for listening.